Alright, thanks for watching, and today I would like to prove the replacement theorem, which in my opinion is the most important fact in linear algebra. It's really the thing that makes all the beautiful statements in linear algebra work. Like if you have a subset of an n-dimensional vector space with n vectors that's linearly independent, then it also spans and it's a basis. But that I have done in another video. Today I want to focus purely on the proof because I planned to do it in lecture, but I ran out of time. So I hope at least you will appreciate it. So what is the replacement theorem? So previously on Peyam Battlestar Galactica, we learned about this beautiful theorem that says as follows. Suppose you have a linearly independent subset of a vector space. So let lin be a linearly independent subset of V with m vectors and gen be a spanning subset, or spanning or generating subset of V with n vectors. And I'll show you in a picture in a second. Then there are two things. First of all, a linearly independent subset can never be bigger than a spanning subset. So m is less or equal to n, and moreover, you can add vectors from gen to lin. In other words, you can extend lin to become a new spanning subset of V. So in other words, there is a subset H of gen with n minus m vectors such that the union of lin and H still spans your vector space. Remember, I had to learn this. I screwed it up a bunch of times. I don't know why. On the midterm, I got it right. I think it's a miracle. But let me just show you a picture. It's actually pretty intuitive. So suppose you have a linearly independent subset with, let's say, 3 squares. So squares always means linearly independent in some sense with m vectors. And you have a generating subset with dots, let's say with 5 vectors here. Then what this says, you can first of all add 2 vectors, so n minus m from gen. Let's say those two, they're really specific ones, such that if you add those red dots to lin, it will be a new spanning set. So in other words, lin union H equals to square, 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 dot, dot. So I forgot to say H is just those 2 dots, red dots. And it has precisely n minus m elements. Why n minus m? Because in the best case scenario, we have m plus n minus m elements, which is best case scenario, it's n elements. So it's either the same size as gen, or if there's some redundancies, it's actually smaller, which might be better actually. Okay, so this is the statement, and in another video I showed you consequences, and now let me prove it. And it turns out what you do it iteratively. And whenever you do stuff iteratively, which I can't pronounce apparently, when you do something step by step, it's usually an induction proof. So let's prove it by induction. Induction on what? So gen, let's say, is fixed. We'll do it on the induction on the size of ln. So we'll do induction on m induction on M, which is the size of Lin. And again, gen will be just a fixed set. So, base case. Suppose M is 0. So suppose Lin actually has no elements. Then Lin is empty. But then in that case, it's very easy. Suppose we have no elements in Lin, then the question is, can we add 5 elements of gen to Lin to still get a spanning set? Well, yes, just choose that set to be gen. Gen has 5 elements, that's what we want, and the union, which is still gen, just spans the set. So, the space. So let H be gen. Then, the size of H, what is it? Well, it's the size of gen, which is n, but that's n minus m, because m is 0. And, Lin union H, which is just empty set union H, which is H. So, or I guess, which is gen, and it spans V. Ta-da! And now let's do the induction part. So, and let me then explain you what's going on. So, inductive step. Suppose Pm is true. That is, whenever Lin is a size of set M, you can increase it. Show that whenever Lin is a bigger set, you can still extend it. So show Pm plus 1 is true. Alright, now here's the idea, and I finally figured it out. That's why I have to do that. So here's the idea. So let's fix gen and do induction on Lin. So let's say gen looks like this. So 2, 3, 4, 5. Suppose we know that we can extend any linearly independent set with 2 elements. So suppose we know how to extend this. We start with 2 squares and we can add 3 dots. Let's see. So let's say those 3 dots. So we know how to do it with small sets. How can we do it with bigger set? So how to extend let's say 3 squares to a spanning set. So suppose this was your original, you can do it was for small Lins, but now you do it for big Lins. Okay, here's the thing. Well, what's the difference between those two? Well, there's this extra square. But this extra square, well, it's in the vector space. Right? Square. This extra thing, it's in V. But V is just a span. We know that this spans. So we know that this spans V. So it's really in the span of this thing. Square, square, dot, dot, dot. Dot, dot, dot. Now here's the thing. Because this is in the span of this, and this is linearly independent, so linearly independent means essential. It means that, well, turns out one of those 3 dots is actually redundant in the sense that we can actually replace this square with one of the 3 dots to get actually the same span. And that's why it's called the replacement theorem. You're replacing one of the squares with one of the dots. So it turns out one of those dots is still in the span of 3 squares and 2 dots. And this is what we're going to show rigorously. So then this implies somehow this thing is in the span of, let's say, 2 squares, and then you add the new one, and 2 dots. And it turns out what's great is this thing is your original set. This will be our new set H. And it turns out we will show that the span of this is the same thing as the span of this, which is just V. So if you let H be this and this are bigger set, then ln union H will still span V. And this is how we can show that bigger sets, they still span the space. Okay, and now let's actually do the induction steps. So this was the, what's it called? This was the idea of the proof, and now let's do the proof. So, I had this epiphany, finally understood why it's called replacement, because you're replacing a square with a dot. So let ln, again, be a big set. It's a set of size m plus 1. So let's call it v1, vm plus 1, and gen be given. And the idea is we want to find h. And so, this is the big set, the stuff with 3 squares. Let's define the stuff with 2 squares. No problem, just kill this vm plus 1. So step 1, let L prime be v1 up to vm. Now, ln is linearly independent. This is smaller than ln, so it's also linearly independent. And gen as above, gen is the same. This is good. We have a smaller linearly independent set. We have a generating set. Bam! We can use the induction hypothesis to extend L prime. So by the induction hypothesis, first of all, the size of L prime is less than or equal to the size of gen. So we already know that m is less than or equal to n, but we want more than that. And also, there is a subset. There's a subset H prime with, again, n minus m elements. Let's call it u1 up to un minus m. G of gen, sorry. Such that the union of L prime and H prime spans V. L prime union H prime, which is V1 up to Vm, U1 up to Un minus M, spans V. And this is super important. We know that this big set spans V. That's the analog of 2 squares and 3 dots. We know that this spans V. Now, one thing. We want to show that n is greater or equal to m plus 1, actually. But what would happen if m equals n? Then h prime is empty. If, I guess, m equals n, then h has no vectors. I'm sorry, then h prime has no vectors. So, the point is, what we then have is that L prime union empty set, which is L prime, spans V. But that's actually a big problem, because what is L prime? L prime is V1 up to Vm. But we also know that there's a bigger linearly independent set. So think of this as being L prime, and this is L. This whole thing, that's Vm plus 1. Well, if this smaller set spans V, then Vm plus 1 is in the span of L prime. Of L prime, which is the span of V1 up to Vm. Why is it a problem? Because we know that the big set L is linearly independent. But L, which is V1 up to Vm plus 1, is linearly independent. And which is a problem because we know that Vm plus 1 is in the span of the previous ones. But this cannot happen, basically. So M is not equal to N, but also M is less than or equal to N. So the only thing that could happen is that indeed N is strictly bigger than M. So N is strictly bigger than M, and because M is an integer, N is greater or equal to M plus 1. Which is good. That's already the first statement of Pm plus 1. So 1 with Pm plus 1. Because that's what we want to show. We want to show that Gen has greater or equal to M plus 1 elements. And we've already shown that. So the only thing we still need to find is this H, our original H. Okay, so here's the second step. So we have this set L prime that's linearly independent, and we extended it with H prime. So just a reminder, this is L prime, and then that's H prime. We expanded that. And so let's just consider the element that's not in L prime. So let Vm plus 1 be in V. Then remember what we have. So L prime union H prime, V1 up to Vm, union U1 up to Un minus M. We know that it spans V. That was star. In particular, Vn plus 1 is in that span. So you can write Vn plus 1 as a linear combo of all the other vectors. You can see it. So there are A1 up to An, B1 up to Bn minus M in any field, so constants, okay, such that your new vector, Vm plus 1, is a linear combo of your old vectors. So plus Am Vm plus B1 U1 plus dot 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 plus Bn minus M Un minus M. Now, what would happen if all the Bi's are 0? Then we would have that Vm plus 1 is a linear combo of V1 up to Vm, which is a problem because, again, we know that L prime is linearly, we know that L is linearly independent. So basically, so B1 up to Bn minus M cannot be all 0. So one of them is non-zero. Let's say the first one without loss of generality. B1 is not 0. And this is the cool part. This is where we take a square and we take a dot and replace it by a square. Because now, since B1 is non-zero, we can actually solve for U1. So this is like where the replacement part comes in. So we then have that B1 U1 is minus A1 V1 dot 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 minus AM VM, and then plus, again, so we take all that on the left hand side, plus Vm plus 1 minus B2 U2 dot 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 minus Bn minus M un minus m. And so solving for u1, because v1 is non-zero, it's minus a1 over b1, v1, dot, 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 minus am over b1, vm, then plus 1 over b1, vm plus 1, minus b2 over b1, u2, dot, 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 minus bn minus m over b1, un minus m. And therefore, again, this dot is in the span of the bigger squares and fewer dots. So u1 is in fact in the span of v1 up to vm, vm plus 1, u2, dot, 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 un minus m. Call this triple star. And again, that's precisely what we're saying. We're saying that the dot is in the span of now 3 squares and 2 dots. So what is our new set H? Is this set, which has fewer elements, which is just what we want. So let H, that's u2 dot 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 un minus m, that's included in u1 up to un minus m. That was original set H prime, and that's so horrible too. And that's included in gen. So it's a subset of our generating set. Moreover, how many elements does it have? Well, n minus m minus 2 plus 1. So H has n minus m minus 1, which is n minus m plus 1 elements. And moreover, if you add H to lim, it spans your whole space. And lin union H, which is v1 up to vm plus 1, union u2 dot 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 un minus m, spans v. And this is because you see the other set spans v. Because the smaller set spans v, so vm union u1 up to un minus m spans v. I think I called it, yeah. That was L prime union H prime. So that's by star. That's one thing. So the idea is, if you let v be arbitrary, then v is a linear combo of those things. But remember that u1 is also a linear combo of all those things as well. So it's okay. Because this and u1 is in the span of v1 dot 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 vm plus 1, u2 dot 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 un minus m. So again, because if you take an arbitrary element in your vector space, it's a linear combo of all those things. Sorry, it's a linear combo of all those things, but u1 you can write as a linear combo of those things. So in particular, you can write everything as a linear combo of those things. So Pm plus 1 is true. Because the point is, this whole space has to span V, and so Pm plus 1 is true, so Pm is true. Peyam is true for all m. This is the proof of the replacement theorem. So one of the things I was always traumatized with and scared of, but I finally understood the proof, so now it's pretty exciting. Alright, so I hope you liked this linear algebra excursion. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.